Hi, and welcome back to Blockchain Fundamentals with Bill Laboon. Today, we're going to discuss a little more about the actual mechanics of Bitcoin. That is, what exactly happens when you send a transaction? What exactly do these blocks look like inside? So first, I want to talk a little bit about consensus. So recall that Bitcoin comes to a consensus with an append-only ledger, or basically append-only via the blockchain. There is decentralized consensus via the consensus mechanism we discussed in the last class. And finally, there's validation of transactions via miners and proof of work. We were discussing last time about how UTXOs work and that Bitcoin does not have direct accounts, but rather uses these unspent transaction outputs, UTXOs, which are consumed in transactions and sent to different addresses. However, there is, of course, an alternative way of keeping a ledger, which is just like a spreadsheet does, an account-based ledger. This would be something like in a block, we create 25 coins and transfer them to a person. Alice transfers 10 coins to Bob and thus gets 10 coins subtracted from her account. Then Alice transfers 5 coins to Carol and gets 5 subtracted from her account. Bob transfers 2 to Dan, he gets 2 subtracted from his account. This is classic double entry bookkeeping. So accounts, if we had some alternative form of Bitcoin that used an account-based ledger, an account which would be still could be delineated by public keys and would have a certain number of Bitcoins. And every time we did a transaction, you would send, you would add a certain number of Bitcoins to a new account and subtract those same number of Bitcoins from the sending account. However, there is a reason that Bitcoin does not use this account-based ledger system. Although other blockchains such as Ethereum do. So perhaps the most important is that if you want to determine if a particular transaction is valid in an account-based ledger, you may have to go all the way back to the beginning of a blockchain. That is, all the way back to the Genesis block. Whereas with a UTXO-based system, you only have to trace back those UTXOs until it got to a Coinbase. That allows us to do things like SPV, or lightweight simple payment verification nodes that are used in Bitcoin. So if you recall, in our transaction-based model, as opposed to our account-based model, every transaction has valid inputs and outputs and can be checked. All of them are properly signed, inputs are consumed entirely, and we always know that the total value of the outputs is less than inputs, with the remainder potentially going to the miner. So when we think of accounts, they're really just a collection of unspent transaction outputs, as opposed to a specific part of a ledger which contains how much value is included, is owned by that particular account. So just as a quick refresher of how UTXOs work, here I'm trying to send 0.1 Bitcoin. So I have an input, one of my UTXOs, I have input as 0.2 Bitcoin. Recipient gets 0.1 Bitcoin. I send 0.09 Bitcoin back, and the 0.01 Bitcoin remaining implicitly goes to the miner. A transaction-based ledger might look like something like this. This is a bit of an abstraction of what the Bitcoin ledger actually looks like. So we have outputs of 25 going to Alice. Then we see that we can trace back. Bob gets, Alice sends 10 to Bob and 15 to Alice. That first output, 1, 0, has been completely consumed, and now 15 has gone to Alice as a new UTXO. For number 3, we're referencing that first output in the second block, 2 sub 1, which is the 10 that Bob now owns, with the output of 5 going to Carol, and then 10 to Alice. Or excuse me, that inputs 1 to 1, which is the second element. Alice has 15, she sends 5 to Carol, and 10 back to herself in change. So if we're trying to determine if something is valid, we actually can just follow the blockchain without seeing any of the irrelevant blocks, because we know we can follow the UTXOs back to where they were initially generated. This is one of the reasons that outputs must be entirely consumed. It allows this calculation to take place. It also allows us to easily do things like joint payments, where here you can have multiple UTXOs from multiple people or multiple addresses that all go to the same or similar users. So here, for instance, in block 3, we can see that the inputs are 2 sub 0 and 2 sub 1, that is Bob and Alice together, but they're sending, so that's 25 coins altogether, but they, in terms of UTXOs, but they're sending 10 to Carol together and then simply getting their change back. However, there are benefits to using account-based models as well. UTXOs give you benefits and account-based models give you benefits. So we've seen the UTXO benefits. They're easy to verify and they easily allow for joint payments. Account-based ledgers, such as that used in Ethereum, offer significant space savings over the UTXO transaction-based model of Bitcoin. They're also much easier to conceptualize because they are, again, just like double entry bookkeeping. They also allow for things like existential deposits. That is, under a certain amount, we just consider an account to no longer exist anymore. That's much more difficult to do in a transaction-based system like Bitcoin, which is why many accounts have what's called dust. That is, a UTXO that is so small that even though it exists at a certain address, it would cost more in Bitcoin to move than it actually consists of. So that was conceptual, how transaction-based models differ from account-based models. So let's take a look at what an actual block looks like. So obviously they are stored internally in a binary format, but I'm going to display them here in JSON, which is the basic key value format. So if you'd like to look at a block, they're generally indicated by either the particular block hash, which remember is going to be the hash of a block, which should start with a lot of zeros since it should be less than a target, or its height. That is, what is the height of this block in the blockchain, where the genesis block is 0 and it increases as more blocks are added to the blockchain. So I have one particular block here from September of 2018. And I just want to note that information in these slides is correct at the slide's creation date. So the block structure of Bitcoin may change slightly in the future, and it has changed in the past. And we'll talk about that a little bit when I compare this block from 2018 to the Genesis block created by Satoshi Nakamoto in 2009. So blocks are going to consist of a few things. The first is the set of metadata, which is information about the block, the size of the block, what its Merkle root is, what the block number is, etc. There will then be a large list, which is an array of all the transactions in the block. There always must be at least one transaction in the block. That Coinbase transaction, which produces the block reward for each block, must always be present. An interesting twist in Bitcoin is that even though this Coinbase transaction must be present, as long as it is less than the current maximum Coinbase, it will also be accepted as valid. So even though a miner is currently entitled to 12.5 Bitcoin for producing a block, if that miner says, you know what, I only want 6.25 Bitcoin or 7 Bitcoin or 2.1 Bitcoin, they are more than free to do this. And in fact, a very famous block once was created, which instead of creating 50 Bitcoin, created 49.9999999. That is, it eliminated 1/100 millionth of a Bitcoin or a Satoshi from their block reward. So this, since that block is since a block reward is the only way for Bitcoin to be created, that one Satoshi will never be added. So actually to the Bitcoin network. This was done as a tribute to Satoshi Nakamoto once he stopped posting on the Bitcoin Talk forum and disappeared. So the creator of the block said that since we are one Satoshi poorer in real life, we can also be one Satoshi poorer on the Bitcoin blockchain. The transactions then section has an entire array of all of the other transactions. They could be zero. A miner could choose not to add any transactions into this block, but you will very rarely see this because miners can also obtain transaction fees by including transactions in the block. And since these, if you remember, all of these transactions get put into a Merkle tree and we're only hashing the Merkle root as that, it really doesn't make much of a difference if they have 100 transactions or 1,000 transactions or 0. So they often, in almost all cases, will add as many transactions as they can, simply to get those extra transaction fees, since it's not any more work for them. So here is an example of some of the block metadata. And I have highlighted in red a few of the interesting aspects of this particular block. So we can see things like the previous block, that is the hash of the previous block, the Merkle root, the nonce, the total amount of fees included in the block, the size of the block. But let's take a look at that hash. You'll notice that it starts with quite a few zeros, 19 to be precise. So remember that when we are generating a block, we need to ensure that its hash is less than some target value. This means that this hash is going to almost always, all cases so far, include quite a few zeros at the beginning because it is a small number. The bigger the number, the larger the number of zeros, the smaller the hash is going to be. So I want you to keep that in mind. There are 19 zeros at the front of this hash. There's the time that it was created. Time in distributed systems is a little odd, since it's very difficult to be absolutely perfect and keep track of time across multiple networks. As they say, a man with a watch knows what time it is, a man with 2 watches is never sure. So the time here is specified in seconds since the epoch, which is the same, the epoch being January 1st, 1970. This is the same system that Unix and most other systems use to keep track of time. This particular block was generated according to its creator on September 23rd, 2018. Note that the generator of a block can modify the time by a little bit, and often they will try different times in order to create a block which hashes to a small value. However, if they try to modify it too much, then by more than 2 hours or so, then you will the other nodes will not accept the block as valid. The number of transactions that were included in this block are 1,236. That's the NTX key. and its height is 542,728. That is, it has been 542,728 blocks since the Genesis block. So let's take a step back 542,728 blocks to that Genesis block generated by Satoshi Nakamoto. So compare this block to our previous block that we viewed. So there were only 10 zeros in front of the hash. It was much easier to produce a hash. The target was much higher than it is nowadays because, as we mentioned, there was much less hash power on the network. The time that it was generated was January 3rd, 2009, which, interestingly, there's quite a gap between the first block being published and when it was actually generated. So Satoshi apparently generated this block and then waited about a week before sending it out. The number of transactions in the Genesis block was 1. It was just the Coinbase. Now, if you think about it, this really makes sense. There were no Bitcoin previous to the Genesis block, and Bitcoin are only generated by the Coinbase. So there was no Bitcoin to send, even if Satoshi had wanted to generate another transaction. And finally, the height is 0. It is the first block that was produced. It is the 0th element. Because remember, programmers like to count starting at 0. So that's the metadata of a block. Transactions, this section is also going to have its own metadata. Information, each transaction is going to have some information about that transaction. What is its hash? What is the number of inputs? What is the number of outputs? Whether or not it is locked for a specific amount of time. Then a list of all the inputs, remember our transaction inputs, that are going to be consumed along with a signature. And then the outputs. So in the output section, there's going to be also a Bitcoin script. So note that in actuality, we're not directly specifying the address, even though we've talked about sending Bitcoin to an address. What we're going to see is a little script written in a language that's just called script or Bitcoin script, which the receiving partner, the recipient it will get sent to them by executing the script. So here's just an example of transaction metadata: what time it was sent, its index, a hash, what block it'll be valid at. That's the lock time. So you can have something, a transaction that won't actually be valid until a future block. This will actually come quite in handy when we talk about atomic swaps a little bit later in the course. So here we have some transaction inputs along with the script that will be run. And then we have the outputs with their script. You can see here that we have the addresses they're being sent to: 1CXPE1T ... and 15JLH7Q ... along with what their values are. So why are we sending things to scripts? We certainly can, from an abstract perspective, send money, send coins, make a cryptocurrency that sends directly to an address. And that is how we were really thinking about Bitcoin in the first few lectures of the course. But Bitcoin is interesting in that it is programmable money. Right? So your transaction is going to specify a script to execute and can do interesting things. Now, that being said, the vast majority of scripts, and when I say vast majority, I mean well over 99%, are just going to move previous transaction outputs to a new address. But we can theoretically do a lot more interesting things with the script language. That being said, most nodes on the Bitcoin network have only a whitelist or allowed list of possible script types. So you can't just run arbitrary scripts on these other nodes. So let's talk a little bit about the Bitcoin scripting language. Unless you're extremely interested in programming something for Bitcoin, you probably won't have to deal directly with the scripting language itself. But I think it makes sense just to go over it and see what's happening and understand why it's happening when you execute a Bitcoin transaction. So inputs contain a part of the script, which is called the script sig attribute. This is going to be the output from a previous script. And I'll show you what that looks like when we walk through this. And outputs contain another part of the script called a script pub key. So if you recall from a few slides back when I showed the inputs and outputs, the input had a script and the output had a script. So when a transaction occurs, this script sig and this script pub key are going to be concatenated and then executed as a single program in script. So script is a very simple stack-based language. Instructions are 1 byte, which means there are only 256 possible instructions, but in actuality, there are much fewer than that. It's not Turing-Complete. It is purposely limited for a variety of reasons, but really to make sure that you don't get into any infinite loops, which remember in a Turing-Complete language, there's no way to verify that the program will cease execution. However, in this case, you will know every Bitcoin script will eventually finish. It has native support for rather complex cryptographic functions, as we'll see. When you see this in Bitcoin, looking at the JSON or the raw bytes for this, there's just going to be like raw hex version. So I'm just like with assembly language, I am going to follow the process of showing mnemonics for this language as opposed to the actual bytecode. But I think it makes it a lot easier to follow than just seeing a bunch of numbers. So first, if you're not familiar with stack-based programming, I think probably the classic way to explain this, I may be required by law to use this example anytime I discuss stack-based programming, is a reverse Polish notation calculator. So in this, every time you see a number, you are going to add it to a stack. When you see an operation, you're going to take the top 2 elements of the stack and perform that operation on those 2 inputs, and push the new element that results from their calculation on top of the stack. So here, a very simple RPN, reverse Polish notation, program 5, 6 plus 4, 3 plus times. So if we think of our stack and we think of time as flowing to the right here, we put 5 on the stack and then we put 6 on the stack. We now execute the plus operation. That's going to take 5 plus 6, so pop the 2 elements off the stack, add 5 plus 6, get 11, and push that back onto the stack. So at this point, our stack just has an 11 value on it. We now add 3 onto the stack, so push that onto the stack, and then push 4 onto the stack, and then push 3 onto the stack. Perform the plus operation. We pop 3 and 4 off the stack, and then push the result of that calculation 7 onto the stack. And finally, we perform the multiply operation. So we push 7 and 11 off the stack, multiply them together to get 77, and push that back onto the stack, we get 77. So the result of this simple RPN program, 5, 6 plus 4, 3 plus times, is 77. So this seems very limiting, right? Why don't we just make it Turing-complete? Well, the big reason is we would never be able to determine if the program could end. And if that's the case, then we could hide some sort of arbitrary length execution program, and any node trying to validate it would get stuck in an infinite loop, thus resulting in a denial of service attack. So as I mentioned, in practice, only a very few kinds of scripts are allowed by most validating nodes. However, note that other blockchains do allow Turing-complete programming languages to be used. Most famously, Ethereum, which has the concept of gas. You pay for every operation. So you can have a Turing-complete language running on the blockchain. But Bitcoin does not do that. So a few script commands: value, so just taking some value and putting it on the stack; opdupe, which will duplicate the top item on the stack. So if you have a stack with a 5, it'll pop the 5 off and then push 5 twice. Hash 160, which is going to be used quite often, which is going to hash the value on top of the stack with SHA-256, then hash again with RIPE-MD 160, and put the final value back on the stack. Op equal verify, which is going to return true if the top 2 values of the stack are equal, otherwise mark it false. And finally, op check sig. Check the input signature is valid using the input public key for the hash of the current transaction. So you can see, unlike a language such as Java or JavaScript, there is built-in support for rather complex cryptographic calculations, like op hash 160. So let's walk through actually executing one of these scripts. So remember, we're going to concatenate script sig, which is from the previous output of a transaction, what sent it to that user, and script pub key, which is the output that the user is going to do to send this Bitcoin on to someone else. So let's execute the script. From script sig, from the previous transaction, we'll get sig and pub key. Our new transaction here is going to have opdupe, op hash 160, pub key hash that was specified, what address we're sending it to, then op equal verify, and check sig. So here is our stack. We're going to put the signature and the public key, then duplicate the public key, run hash 160 on it to get an address, get our address that we specified when we were sending this, and then op equal verify. So did both of these, did the potential public key hash meet the public key hash? The only way this will occur is if the the user who was sending the Bitcoin had access to those coins and was sending it to a valid address. If they didn't, then op equal verify will fail, and this Bitcoin transaction will be considered invalid rather. Otherwise, that pub key and sig can now be used for a future transaction, just like we got the pub key and sig, which we saw at the beginning of this initial transaction. So again, every time you are sending Bitcoin to someone else, you're actually executing a version of this script. Another thing that you can do with a Bitcoin script like this is proof of burn. So proof of burn verifies that you have a UTXO or some part of a UTXO that is destroyed, that will never be spendable. And how you do this is you're going to add an op return opcode, and the script will always return false. So you have sent that Bitcoin, but this particular opcode means that it will never be spendable. It is now burnt. So why would you do this? So probably the most common use for this is to get tokens on another network by burning some of your Bitcoin, by proving that I no longer have access to this Bitcoin. This was most famously done probably with the counterparty token in 2014, where you could burn some Bitcoin and get a counterparty token. Now, why would you not want to just send that Bitcoin or use it to someone else, send it to a charity? Well, you never know who actually owns that charity, if it's a front for someone else, or if the people starting this new token are just using it as some sort of scam to get more Bitcoin. If you want to make sure that it's difficult to get the coin, whatever new coin you're producing or whatever it is that you want to do with that, but you also want to prove that you are not getting anything from that because those Bitcoin are burned, then you can use proof of burn in your scripts in order to verify that people are getting rid of their Bitcoin, but that doesn't mean that you are going to take it and perhaps do something malicious with it. The last thing I wanted to discuss on this topic is the different ways that you actually can specify the receiver of your Bitcoin. There are a few different kinds of these ways to pay. Perhaps the most famous is P2, or most used is P2PKH, which is pay to public key hash. So if you remember, addresses are actually the hash of a public key. So really, this is like pay to address. It's probably the most commonly used. There's also P2SH, pay to script hash, where if you have a complicated script, you actually, instead of paying specifically to an address, you can pay to a hash of a script. This was not part of the original Bitcoin specification. It was added in 2012. But it allows more complex transactions to take place by directly sending them to a script. There are a few other transaction types besides these more common ones. There is pay to public key, where you would specify a public key instead of a public key hash, or what is now usually called an address. This was really only used in the very early days of Bitcoin and actually has not been supported in the Bitcoin Core client for many years now. But if you start spelunking in the early blockchain, you'll see a few of these floating around. There's also P2WPKH, pay to witness public key hash. These are SegWit transactions, segregated witness. This is a new kind of transaction which appeared in 2016, which we will discuss a little bit later when we talk about the Bitcoin Cash split. So that is all I have to say about the mechanics of Bitcoin. There is a lot, obviously, that you can dig into here, and obviously just scratch the surface of the Bitcoin scripting language and exactly how blocks are constructed and what all keys and values they consist of, etc. There is a really, for the interested student, there is a lot to dig into here. When we show up for our next lecture, I'll be discussing more about mining in today's day and age and how it is actually done and how it differs from the early days of mining.